Okay, so next page, I have kind of a nice little application and then one other theorem based on MVT. This is a review. MVT says instantaneous rate of change must equal the average rate of change over the interval at least once. Now let's see, excuse me, a little application of this. So a toll road has a speed limit of 65 miles per hour. A trucker handed in a toll marker at the end of the 139-mile toll road. So you know, like sometimes when you get on these toll roads, you get a paper, and then at the end you have to turn it in. That's how far you travel. You might have to pay that amount, a certain amount for how far you traveled. She covered it in 2 hours. She was cited for speeding, and what? What? Yeah. Well, we can use MVT here. I guess we're assuming a closed 2 hours, like 0 to 2 hours. You know, like didn't stop, basically. 0 to 2 hours. We assume, again, continuous, like she didn't stop on the road as well. I'm just going through the conditions. And therefore it's differentiable. Perhaps we don't have really a function to base that on. So, but anyways, it meets the conditions where we can try to apply the MVT. So the MVT, the AROC must equal the IROC at least once. So the AROC here, the average rate of change. Average rate of change. Well, she went 139 miles distance in 2 hours. So the rate is going to be distance divided by time. The average rate of change, I should say, between 2 points is the distance under this one. Divided by time, so it's miles in 2 hours. So let's see, 140 divided by 2 would be 70. So this should be 69.5 miles per hour. So that was the average rate of change. Average rate of change. So that's all we need to do is instantaneous rate of change kind of implied in here. Why would she be cited for a ticket? Well, her average speed, right? Average rate of change is 69.5. The speed limit is 65. Well, the MVT says that she must be going this speed at least once. Right? Clearly, we know if that's the average, probably higher than that sometimes, maybe lower than that sometimes. But she must hit. MVT says must hit this at least once. And I'm talking about her. Like if you look at the speedometer, that's the instantaneous rate of change. That's what that tells you, what you're going at that moment. That's it on this one. I'm just saying, okay, her average rate of change, MVT says, well, the IROC must be equal to that at least one time. So she must have gone that at least once and broken the speed limit. So.
Do you think like 4 miles over is considered speeding?
Yes. 0.1 miles per hour over is speeding. Keep that in mind, right? You, a young driver.
Like
If
do
you
think
go
she-
like
do you
5
think you should get a
over,
ticket
they're not going
for
to
it?
give you a ticket.
Now that's up
Going
for
like
debate, okay? But
5
I'm just
less
saying.
over. If you go about 5 over, you're good.
Is that the rule?
Just don't go about higher than that.
Who told you that?
Just know.
Whenever Terry gets pulled over, that's what they tell you. Yeah, I've heard that too. I've also heard there's some like speed traps where if you're like 1 mile per hour over, you'll
Over in like Shawnee Hills, kind of like Dublin area, they have that thing on lock. It's crazy. I've never like driven through there, and there's not at least like 3 cops just like posted up, just like trying to catch speeders.
I think I know where you're being. I don't know if I've ever traveled through that. I'm not
Yeah, there's
going
like
to
an
now.
Elvis Row nearby and stuff.
Well, sounds good. Back to Rolle's, so MVT. I'm going to talk about Rolle's theorem. It's actually like underneath, kind of subcategory of MVT. Rolle's theorem is just a special case of the mean value theorem. And here, what should I say? F of A equals F of B. In other words, the Y values are the same. So here's a good example. It is just mean value theorem. You can do the same thing as normal. Okay. But what Rolle's theorem said, I forget why. I think this guy Rolle came up with this theorem separately. What I'm saying, while somebody else had the mean value theorem, and then at some point they discovered like his was just a special case of the mean value theorem. I think that's what it was. So let's say we're on this interval AB. Well, look at this graph. A and B happen to have the same Y values. That's what this says. If f of A, the Y value at A, and the Y value of B, f of B, if they're the same, well, the secant line would be a slope of 0. And so what this says is if the Y values are the same, well, the same theorem is true. Everything, continuous function, closed interval, differentiable, same A rock equals I rock at least once. But we know that the derivative, the I rock must be 0. Okay, the other ones we didn't know. It might have been like this, where it was a different slope. This we know the slope is 0. Everything else is the same. Yeah. So let's just try an example of this. You're going to see I'm basically going to do the same as what I've been doing before. So Rolle's theorem, still need the same conditions. We're on a closed interval over there, -2, 2. This function, polynomial. So any polynomial, continuous and differentiable everywhere. Let's see. So I'm going to basically approach it the same way. I'm going to do A rock and I rock. And you'll see right here when I do the A rock, because it says verified Rolle's theorem, we know it's going to be, the Y values are going to be equal here. So I do f of b minus f of a, f of 2 minus f of -2 over b minus a, 2 minus -2. So it's 2 plus 2, so it's 4 on bottom. Then I just gotta go plug these in. 2 plugged in. That'll be 16 minus 2 squared, 4. So you get 12. Without doing any work, I know the next one's going to be 12. Because the Rolle's theorem, these are the Y values. So I plug in -2. -2 to the 4th is still 16. Minus -2 squared is also still 4. So it's 16 minus 4 is still 12. So it's 0 over 4, which is 0. So I say just do the same work as before. However, you also could have just separately, you could have said f of 2 is 12, and f of -2 is also 12. And you therefore could have just concluded this, that the secant slope will be 0, because it's the same Y values for your endpoints. So if you saw that, you didn't have to do this, but I think it's just the same amount of work to do that.
With Rolle's theorem, it'll always be 0.
Always be 0, yeah.
So, like, we'll get a question on the test, and we know we just have to work it out until it's 0.
Yeah, pretty much. What was I gonna say about that too? Yeah, and it's, you know that it's gonna be 0. It's just, maybe at least you should show this. Like, all right, I plug in the endpoints and I get the same number. So that means the Y values are the same. The secant slope is the same. So when you, and so this part would be the same number as well. But yes, you're right. So I do the derivative for the IROC, and let's see, it's 4x cubed minus 2x. Okay, and then AROC will equal the IROC at least once. And so I set this equal to 0. I'm basically finding a horizontal tangent. This is basically what we did with max and min so far. Right? Derivative equal to 0. So it should look pretty similar. So 4x cubed minus 2x equals 0. I'll factor out a 2x. And so we'll be left with 2x squared minus 1. Alright, so I set each of these equal to 0. When I set 2x equal to 0, I can divide by 2 and get 0. 2x squared minus 1 equal to 0. I can add 1 and divide by 2. So x squared equals a half. And then I can do a square root. So I get plus or minus. Let's go ahead and write it in simplified form. So square root of 1 would be 1, right? And the bottom would be square root of 2. Then we can rationalize. So times radical 2 over radical 2. So it'll be 1 radical 2 in the numerator over radical 2 times radical 2 is radical 4, which is 2. So those are the three values for this function where the AROC equals the IROC, and really where the IROC equals, where the slope is 0. So for this function at 0, at x equals 0, x equals radical 2 over 2, and negative radical 2 over 2. Because it makes sense too, this function is x to the 4th, so it's going to look, w-like. And so at 0 here, it'll have a slope of 0 at this value and at that value. There's 3 spots where the horizontal tangent, where the slope is 0. Okay, so that's it for Rolle's theorem. Again, just a special case of the mean value theorem. Anything you can answer? Questions on those? Okay. Well, let's work on the MVT practice.